We went through the copper zinc galvanic cell, and this is what we ended up with. Very busy on that screen, but I did highlight a few things. First, the standard cell potential difference between the two of them is positive 1.10 volts. And when I look and see how I have it hooked up, because right now I'm forcing the meter to give me a positive value, I see that the electrons are being produced at the zinc ion electrode, which is the anode, and they're traveling over to the cathode, which is the copper 2 ion. Now that cell potential of positive 1.10 volts, big problem, because you can't assign that to either half cell. That's for the whole cell. You cannot measure half cell potentials. They have to be measured together. Oh, we have to figure out what to do about that. I'm going to swap that zinc electrode out for a silver one. Let's see what happens. And we also went through a copper-silver galvanic cell. And this is what we ended up with. Differences. The standard cell potential is now positive 0.46 volts. And then when I look at the setup to see how I got the positive value, it means that the anode is now the copper 2 ion electrode. When it was paired up with zinc, it acted like the cathode. Now when it's paired up with silver, it's acting like the anode. So the electrons are being produced at the anode, going over to the cathode, and the cathode is the silver ion half cell. We need to have a reference. What I mean by reference is when you go into the lab and you weigh something on the balance, you probably put a piece of weigh paper or a plastic weighing dish down, and then you tear the balance. Now that weighing dish or that weighing paper isn't really 0 grams, but you've reset the balance so it reads 0 grams. So when you weigh something out on there, the mass difference between the substance and the paper is whatever it is on the balance. So that's what we're going to do. We're going to make our reference electrode the standard hydrogen electrode, and then hook up all of our electrodes to this one and take measurements and figure out what to do with that. This standard hydrogen electrode, it has a constant supply of hydrogen gas at standard conditions, which means we'll take it as 1 atmosphere. It's being bubbled up through a solution, and the solution is acidic, and under standard conditions, we'll take that to be 1 mole per liter of hydrogen ion. And that platinum rectangle there in the center, that dark gray one, platinum is inert in this reaction. What it does is it provides a place for the reaction to occur there on the surface. Just like before, a half cell can act as a cathode and it can act as an anode. It just depends upon what you hook it up to. If this electrode acts like an anode, what will happen is hydrogen gas will be oxidized into hydrogen ion. If it acts as a cathode, it's being reduced, then the hydrogen ion in solution will be reduced to H2 gas. Now all we have to do now is hook this up to all the different half cells and see what we get. So we'll hook it up one at a time to our copper, and then to our zinc, and then to our silver setups. Let's hook it up to copper first. So I have a copper 2 ion half cell there on the right. I'm going to make all my electrolytes nitrate solutions now, and my salt bridge is going to be a nitrate solution just because nitrates are soluble, so I like using those. So when I have this hooked up, I look at my meter and I make sure I get a positive value, and so the standard cell potential is positive 0.34 volts. That's the difference between the standard hydrogen electrode and the other half cell. When I look at the setup and I see how the meter's hooked up, I realize that the electrons have to be coming out of the standard hydrogen electrode, traveling through the wire, going over to the copper 2-ion electrode, which makes the standard hydrogen electrode the anode and the copper 2-ion electrode the cathode. So the half reactions for both, we wrote earlier that the half reaction for the standard hydrogen electrode oxidation is hydrogen gas being oxidized into 2 aqueous hydrogen ion. And then at the cathode, the reduction half reaction is copper 2-ion aqueous being reduced to solid copper. We are not there yet as far as you being able to figure out what the half reactions are. I mean, you might be able to, but we're going to do something here in a little bit. Not in this presentation, but so these 2 half reactions are gifts. And then if I want to balance them together, balance the electron flow, same number of electrons in as go out, common number of electrons. And I see that for both half reactions, it's 2 in, 2 out. So that's good. So just add up the half reactions. I add up the reactants, and I get hydrogen gas plus aqueous copper 2-ion. I add up the products. I get 2 hydrogen ion plus copper solid. Okay, so in this one, remember the copper electrode is acting as the cathode, and the standard hydrogen electrode is acting as the anode. And that 0.34 volts belongs to that overall reaction written there at the bottom. Let's swap our copper out for zinc, and we'll use a zinc nitrate solution for our electrolyte. And the cell potential difference between the two of them is 0.76 volts. And the zinc ion half cell is the anode, and the standard hydrogen electrode is the cathode. Again, you look and see how the meter's hooked up. You see which way the electrons are flowing. So the reduction reaction for the cathode is 2 aqueous hydrogen ions being reduced to H2 gas. And the anode half reaction, that's oxidation, that's zinc solid being oxidized to aqueous zinc ion. I want the overall reaction. So take those 2 half reactions, put them together, balance the number of electrons in and out, 2 and 2. Oh, that's good. Now just add them up. Add the reactants up. That's 2 aqueous hydrogen ions plus solid zinc. And that's reacting to make hydrogen gas and aqueous zinc ion. So the standard cell potential of 0.76 volts belongs to this overall reaction. We did copper, zinc. Now let's do silver. Silver and silver nitrate. And you read the meter. And you go, oh, all right. I made sure it's positive. Good. And it is 0.80 volts. The hydrogen electrode is the anode, because you see where the electrons are coming from. And so the other electrode must be the cathode. At the anode, oxidation, that's H2 gas reacting to make 2 aqueous hydrogen ion plus 2 electrons. And then reduction at the cathode, that's aqueous silver ion plus 1 electron reacting to make solid silver. For the overall balanced reaction, balance the electron flow when you put half reactions together. I have 2 electrons and 1 electron. The common number of electrons between the two of them is 2. Which means I have to double the cathode reaction. So H2 gas plus 2 aqueous silver ion. That reacts to make 2 aqueous hydrogen ion and 2 solid silvers. Remember, the cathode reaction is being doubled. And the cell potential of 0.80 volts belongs to this reaction. The thing we need to do next now is we need to come up with a set of values for half cells. Remember what I said, weigh paper. Think of the standard hydrogen electrode as weigh paper. That's what we'll do next.